you, Sander, for the introduction, and thank you all for coming to my talk. I'm Robert. I am a data scientist at Go Data Driven, and this is my first ever conference talk, so please send me some of that first-timers lovin'. So who here is familiar with Reddit? Yeah, all right, so most people in the room. That's good, that's good. Great, so most of you have probably run into posts like this one. So you see some text, story like Research Institute, blah, blah, mouse surgery, blah, blah, felt a little high, leaks in the isoflurane chambers, blah, 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 lab manager chewed out the postdoc, blah, blah, blah. And then at the very bottom, you see TLDR, recreational drug usage taught me to recognize anesthesia leaks. So for those of you who are not really well versed in internet speak, TLDR stands for too long, didn't read. Now that is, we have a long, possibly rambling story, and then it's capped off with TLDR, and then a pithy recap of what the person just wrote. So this is an example of what's called an abstractive summarization, which is a type of summary created by first digesting a long piece of text and then generating a new, original, shorter version of that text. Now this is a task that for most humans comes quite easily. I think I wrote my first book report when I was about 9, but it's an open research problem in the machine learning community. Now, if you spend a few more hours at work on Reddit, you're likely to come across something like this, which is a post by user autotldr, almost always in response to the posting of a news article, with a cohesive summary of the article and the admission that the author is in fact a bot. That's right, so user autotldr is a computer program and is able to generate coherent text summaries, despite what I just said about summarization being an open research problem. So you might ask yourself, how is that possible? And it turns out that there's another approach for generating summaries called extractive summarization. And the idea here is that instead of generating your own original summary, you just want to find a few sentences in the original text, which, when concatenated together, convey the main ideas of the original text. And now that might sound like a silly idea, and you may not expect that to even work, but recall that what we were doing back in our high school days when we were preparing for exams. We were reading our textbooks, we were highlighting key sentences as we were going along, and then the night before the exam, when we were cramming, we would just reread only those sentences in order to refresh our memories about what the book was about. Now, from a programming perspective, this technique has a lot of advantages. Because this technique doesn't require the generation of original text, which would require a deep model of all the things which make language difficult, like syntax and grammar and style. The summaries our extractive algorithm outputs will automatically read like they were penned by a human author, because they were. Or at least the individual sentences within the summary will sound like they were written by a human. Additionally, for certain information-dense media, and in particular for news articles, this approach has a decent shot at working because these media by nature don't smear concepts like character, motivation, or personality across multiple paragraphs, which require a model of abstraction, which is also incredibly difficult. So now it turns out that in contrast to the state of research in abstractive summarization, we're at a point where we can write software that can generate extractive summaries automatically and have been doing so for roughly 15 years. One particularly effective algorithm for generating extractive summarizations, which is the technology behind SIMLI, which is in turn powers autotldr, is TextRank. And that's what I'd like to discuss with you today. So to begin, I'd like to start with the takeaways from my talk. One, TextRank is an algorithm that can be used to make extractive summaries of text and is natural language agnostic, which means that it doesn't really care what the input language is, although implementations of this algorithm certainly are. GenSum is my recommended Python implementation of TextRank for English text, and GenSum can be modified to work for a number of other languages, and I'll talk about which ones towards the end of my talk. Got it? Okay, good. So now for the details. Here we see TextRank bringing order into text. It was written by Rada Mielchea and Paul Tarau in 2004, and it was a product of its time because just 6 years earlier, Sergey Brin and Larry Page had released their paper, The PageRank Citation Ranking, Bringing Order to the Web, outlining PageRank, the algorithm that formed the basis for Google's original search engine. which in 2004 had already established Google's preeminence over the then darlings of the search world like Lycos and AltaVista. And I'm probably dating myself by even acknowledging I have knowledge of Lycos, let alone had ever used it. Now, Brendan Page's insight was that if you were to view the World Wide Web as a mathematical graph with nodes representing websites and edges representing websites pointing to one another via hyperlinks, the structure of that graph contains all the information necessary to determine the relative importances of each website. That is to say, the importance of a website could be indicated in some relative way based on its relationship with other websites, and not per se in some absolute way based on text and tags forming the content of that website. And now as a side, and I'm really going to date myself when I say this, back in the early search days, websites used to game content-based search systems by writing popular query terms in the backgrounds of the website. So the background of the website would be yellow, and you'd write things like Yahoo, 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 Yahoo 1,000 times in yellow over that background. So I had a side job at Google where I had to check a website by literally pointing my website, my browser at these suspected websites, and then press Control-A and see if anything suddenly popped out in the highlighted text. But anyway, so this relative importance could then be used to rank hits to a search query. So if you had two websites with the same search signals, the one with the greater importance would be ranked higher. And it's, we all know how that worked out for Google. So how does PageRank work? Well, first, you make a graph node for every web page publicly accessible via the World Wide Web. 2, if one website links to another, you draw a directed edge between their respective nodes. And 3, for each node / web page, you calculate an importance weight based on the graph data. And so the question becomes, how do you calculate that importance weight? So the essential basic idea is that the more websites that link to your website, the more important your particular website was. So for instance, in this illustration where the size of the node represents its importance, the green nodes are all of lesser importance because no other website points to them, with the exception of that guy on the left side, but we're not going to worry about that little guy. And the yellow node here is very important because lots of different websites point to it. Now, except if that were it, this would be a really fragile system. For instance, setting up 1,000 cheap websites to do nothing else except link to your personal web page would be a way to game the system. So what Brin and Page did instead to account for this was to also account for the backlinked websites' own importances to weight that edge count. So in particular, that's why the red node there at the top is so large. There's only one link going to it, but that link is coming from a really important website, therefore also making that red node important by association. So more specifically, every website's importance was evenly spread across its edges so that if you were a website and you had 3 outgoing links and you had an importance of 3, you would contribute 1 unit of importance to each of those linked websites. Now, if you've been following me so far, you've probably noticed that this importance calculation is recursive. You need to know the website's importances in order to calculate their importances, which sounds like a case of the dragon eating its own tail, but one can show that there's a straightforward iterative process for solving for the importances, which I'll illustrate with a toy example. So here we have a toy internet where we have 4 websites. Website A points to the other 3, websites B and D both point to 2 other websites, and website C points back to A. Now you start with this graph and you take their their directed edges, and then you create a system of linear equations from them. So here these unknown variables are simply the unknown importances for each of the websites, and these fractions represent basically how many outgoing links each of these websites had and where they went to. We take our linear equations, we make a matrix formula out of them, where this matrix here is this adjacency matrix, what I was talking about. And then if we rewrite it like this, it becomes clear that we have an eigenvalue problem. That is to say, we're looking for a vector which, when multiplied against that matrix, is itself. Now, the math tells us that if we start simply with a vector of 1s, multiply that against our adjacency matrix, take the result of that, multiply it again against the adjacency matrix, and we keep doing that over and over and over again. Eventually, the resulting vector will stabilize to some values. And when it does, then we'll have our vector of importance weights for all of the websites. Sergey and Bryn and Paige called this the PageRank vector. And now this solving process comes from dynamical systems theory, but it also lends itself to a nice probabilistic interpretation. That is to say that the node importance is also the probability that a random internet surfer will end up on your website. And perhaps the way you can see that is with that initial vector of 1s. We're sort of putting equal drops of probability at every website, and then it just flows through the network of our graph over and over again until it's sort of reached a sort of state of equilibrium. Now this interpretation comes in handy when your directed graph is such that there are nodes from which a surfer can't escape because they have no outgoing links, or that there are connected components such that you can't reach the one from the other. So say you have one node, it has 2 outgoing links, and then from those links you sort of end up in little loops. In this situation, the solving technique will give ambiguous results. So what Bryn and Paige did was they introduced the chance that the surfer, instead of moving from one website to another via a link, would simply skip to another link. And intuitively, maybe that makes sense to you as well, because if you've just got stuck in a circle of 3 links, at some point you get bored of following links and just try something new at random. So if you take that into account, then your final equation starts to look like this, where we still have our adjacency matrix A, and we have this new constant matrix B, and we've introduced a damping factor D, which is the probability that the surfer will at random skip to some other website. Through their experiments, Paige and Bryn determined that a decent value of D was 0.15, so 15%. And now our iterative solving process now works with all sorts of network topologies, and that's it. But you're not in this room to hear about PageRank, you're here in this room to hear about TextRank. So what precisely is the connection between the two? Now Milhalchea and Tarot, remember these are the authors of the TextRank paper, realized that a piece of text could also be seen as a graph, to which one could also apply the PageRank algorithm. So how do we represent our text as a graph? First, instead of the nodes of our graph representing websites, they now represent individual sentences. Secondly, instead of the edges of our graph representing hyperlinks pointing from one website to another, we now have sentences referring to one another in some way, which will become clear later in the talk. But whereas a website has a definite set of other websites to which it links, the set can't immediately set about sentences. And as a result, whereas once we had a sparse graph, we now have a dense graph. That is to say, all nodes connect to each other. However, here we have to treat the edges differently than we did in the PageRank case. Why? Well, whereas a website is selective in the websites in which it chooses to link to, and therefore to first approximation, all the outgoing edges can be equally weighted, the same doesn't hold for a sentence linking all other sentences to it in a text. Surely some connections are more relevant or important than others, and certainly some connections are completely non-existent, which means we need some way of weighting our text graph edges. The approach taken by TextRank is to first apply some measure of similarity between the sentences and then to use that as the edge weight. Thus, the TextRank algorithm consists of 1. Make a graph node for every sentence in the text. 2. Draw an edge between every pair of nodes. 3. Calculate weights for each edge using our similarity measure. 4. Calculate for each node sentence an importance weight via the PageRank technique. Now notice in this algorithm that this algorithm is natural language agnostic, which means that at no place did I actually specify any technique which is dependent on the characteristics of a particular language, such as English. Where a choice of language comes into play is when you actually try and implement this algorithm, and that'll be the focus of the next section of my talk. And that's it for TextRank. To create an extractive summarization tool using it, you add 2 additional steps. First, you have to actually parse your text into sentences, and that's more difficult than it looks. And lastly, when you're done, you simply order your sentences in decreasing importance, concatenate them until you reach some sort of pre-specified word limit. Precisely this is done by the Python module I want to tell you about next, which is Gensum. So who here has used Gensum before? Great. So those of you who have used Gensum probably You discovered it because at some point you were looking into topic modeling, and you discovered that GenSum is this really nice distributed LDA implementation. The second most probable reason that you were investigating GenSum is because it also has a nice set of word vectors available. But what you might have overlooked in GenSum's API is its text summarization feature. Here, text is simply the string we'd like to summarize. Ratio and word count are the ways we set the predefined word limit on our eventual summary. And split provides this option for outputting your ranked sentences as a list, as opposed to some sort of concatenated string, which can come in handy if you need to use each of these individual sentences in the right order for some future downstream purpose, or if you don't like separating your sentences with a single space. Now, summarize is the implementation of an algorithm, and so the first question one might ask of summarize is, what choice of sentence similarity did GenSum make? If we were to look back at the original paper, the authors suggested this following, which is a bunch of math, so I'll just tell you what it means in English. First, you take your two sentences, you try and find words which appear in both of those sentences, you count how many of those words there are, and then you normalize that count in some way by the total length of the two sentences. The similarity measure has a few properties we like. For one, the greater the overlap in words between the two sentences, the greater the similarity. Secondly, if that overlap actually represents a small percentage of all the words in the two sentences, the similarity is penalized. And lastly, it can be 0 if two sentences have no words in common, thus reducing the size of our graph and thus the computational complexity of the sentence importance calculation. However, GenSum made a number of design decisions to improve upon this measure. So recall that the goal of here is to be able to develop some sense for whether two sentences refer to one another, or put the other way around, to better discern whether two sentences are completely not referring to one another. So towards that second goal, one thing we can do is, before doing any of the math, first strip out all of the words that dilute our ability to distinguish between two sentences. And in particular, we can remove stop words, or extremely common words that don't do much to distinguish the informational content of a piece of text. Here we see the actual stop words used are hard-coded into GenSum, and for those of you unfamiliar with frozen sets, they're simply immutable sets, which are useful for making sets of sets. Stripping stop words also has the additional benefit of setting the similarity of two sentences to 0 that don't share any concepts, but perhaps both include the word the. Now, to be fair to the authors of the original TextRank paper, they did suggest that instead of looking at all words in the sentences, you simply look only at the nouns and the verbs. And this, to a fair extent, is similar to stop word removal. However, this approach would still give equal weight to all remaining words, and we can easily imagine situations where some words might be more important towards our goal of distinguishing two sentences than others. Which leads us to GenSum improvement number 2, which is to do away with the originally proposed binary word indicators and instead weight the presence of a word in the context of a sentence that appears in, and also in the context of all words appearing in all sentences in the text. So specifically what I mean, as a first step, we can weight the words that appear multiple times in a sentence more heavily. And second, we can penalize words that, while not stop words, nevertheless occur frequently in our text. And these types of words tend to arise due to being domain-specific words, such as money in a text about banking, or player in the context of a corpus of football texts. So more specifically, each word in each sentence receives what is called a TF-IDF score, so term frequency inverse document frequency score, which is the product of the number of times a word appears in a sentence and 1 over the frequency with which it appears in any one sentence. That is its inverse document frequency. So our similarity score then becomes the following. Again, math, but I'll just say it in English. Again, I'll look for all the words which appear in both sentences, and then take the product of the TF-IDF scores of those words, and then sum up those products. Again, by normalizing by some factor. And as a side note, what GenSum actually does is calculate not the TF-IDF score, but something called the BM25 score of each word, which is almost the same, except that it modifies the term frequency calculation a bit such that it saturates, such that the more it appears, the less of an influence that has on the overall score. And that saturation point varies depending on how length your sentence is in regards to the average length of the sentences in your text. So if your sentence is shorter than average, that TF score can saturate more quickly. Now, by switching over to TF-IDF scores instead of using the binary indicators, we've now introduced a way to not only measure the overlap between two sentences, but also how relevant that overlap is in the context of all sentences in the original text. However, this approach has one major deficiency, namely that this measure only increases when the exact same word appears in both sentences. This can lead to situations where two sentences both have to do with the same concept, in this case the concept of running, but because one is she runs and the other was they were running, their similarity according to our measure is precisely 0. So what we would like is some representation of both sentences where the verb appears in some common form, say run. And we can imagine lots of situations like this. For instance, fishing, fished, and fisher could all be represented by fish. Consisted, consistency, and consistently by consist. And argues, arguing, and argued by argue. Note that we don't actually require that that representation be an actual English word. And there are a few approaches to addressing this problem. For instance, we could have some complicated lookup function which replaces was, were, and is with be, the verb of existence. But these are relatively computationally expensive. It turns out that one can actually get quite far by simply taking a word and then chopping off the end of it in some intelligent way. And this process is called stemming, and it is GenSim improvement number 3. So what does that look like? Here we see a sentence and its result after having been passed through GenSim stemmer. Note that it is far from perfect. For in particular, quite has been reduced to the unrelated quit. But because stemming algorithms are all rule-based and quick to execute, it makes a nice balance between increasing the chance of recognizing a matching concepts between two sentences while not incurring too great a computational cost. And that's GenSim's approach to sentence similarity. To recap, first, remove all stop words from all sentences and focus on words that better distinguish between two sentences. 2, stem the remaining words to increase the similarity between two sentences with words differing only in inflection, but being the same in concept. And lastly, calculate similarities for all sentence pairs using token TF-IDF scores, or really BM25 scores. And there's one other non-text rank-related trick that GenSim has up its sleeve. Turns out that breaking text up into its component sentences is a non-trivial task, something I alluded to earlier. And in particular, the dot symbol, or the period, because it can take on so many different meanings in English, can fool an automated splitting algorithm. So GenSim approaches this by using a pair of regexes to ignore most abbreviations of titles, like Mr. and Mrs., and also for ignoring acronyms, like NASA. And that's it for GenSim's implementation of TextRank. Now, in my opinion, GenSim does a great job summarizing short text, and in particular news articles. But it should come as no surprise that it only does really well with English text. After all, the stopword list contains only English entries. The stemming algorithm used was designed specifically for the English language. And the regexes it uses to deal with the dot symbol is optimized for English grammar. But because you and I understand now so well why GenSim is successful with the English language text, and because GenSim is an open source project, we can open up the hood, rip out all the English specific bits, and replace them with their equivalents in our favorite non-English language. So let's start with the easy bit first. We need a stopwords list. So we visit our friends over at Stopwords ISO, find the repository corresponding to our non-English language, and borrow their list, being sure to give them appropriate credit. I count 57 different languages, and in addition to all of our Western European friends, there are also stopword lists for languages such as Indonesian and Afrikaans and Kurdish and Bengali, etc., etc. This is the repo for the Dutch language. At the bottom, you see stopword lists in both JSON and text format. All you have to do is bundle them up and then drop them into GenSim's pre-processing file. So you just strip out that frozen set with the one from Stopwords ISO. Next up, we have to pick a stemmer. There are a large number of them in NLTK's stem package, amongst which is a particularly fast set called snowball stemmers. You'll find stemmers for Arabic, Danish, Dutch, English, Finnish, French, German, Hungarian, which I think I'm supposed to call Magyar, Italian, Norwegian, Portuguese, Romanian, Russian, Spanish, and Swedish. Using one is simply a matter of including NLTK in your environment and replacing Jensen's Porter stemmer class with your choice of stemmer. In this case, I've chosen to use NLTK's Dutch language snowball stemmer. And I mentioned a number from NLTK. There are a number of European languages missing from that list, mostly from the Slavic family of languages. If you just Google around, you'll find results for stemmers in these languages, so it's not really impossible. The thing is that they typically are in Java, so you have to translate that logic yourself to Python. Slightly further afield, you have like Turkish, which has a suffix-only agglutinative language, lends itself well to stemming. Indeed, one finds Turkish stemmers quite easily on the internet, I think also in Python. But in general, just because it's not supported in a major Python project doesn't mean it doesn't exist or it's not possible. It just means it requires more work, either translating Java to Python code or poking around the websites of NLP research groups at a university in the country whose language you'd like to summarize. Note that although NLTK has a large number of stemmers, in particular non-European ones, there are a few notable exceptions. First and foremost, because it isn't a character-based language, Chinese text summarization does not seem to be possible via our BM25-based sentence similarity measure. Less obvious choice would be Hebrew, and that's in part because its written form typically doesn't include vowels. But I hope there's enough here to make most of you in the room happy. Lastly, in principle, we should also swap out those abbreviation regexes I mentioned, and additionally add new ones on a case-by-case basis specific to the language you'd like to summarize. I haven't been able to find one library which provides these things, so you're probably just going to require the services of somebody with a domain knowledge of that language. So that's all well and good in principle, but I actually went ahead and did this one for Dutch on an afternoon project. I call it SAMENVATTR, which is a 2007 play on words for the Dutch word for summarization. And you can view what I did at my GitHub. Again, I want to emphasize that the lion's share of the work was done by the lovely people at Gensum. All I did was simply glue all the pieces together. Now, as this is a data conference, I would normally want to show you some examples of what I did, but given the medium of a presentation and that not everyone in the room necessarily speaks Dutch, skip that. But if you're interested, you can simply clone my repo and then try it out on the morning newspaper tomorrow morning. And that's my talk. To conclude, I'd like to throw the takeaways back up on the screen once more. So text rank is an algorithm based on page rank, and it can be used to make extractive summaries of text that is natural language agnostic, although the implementations of this algorithm are not. Number two, Gensum is my preferred Python implementation of text rank for the English language. And three, Gensum can be modified to work for a number of other languages. Check out my SAMENVATTR for an example in Dutch. Thanks for your attention, and I'd be happy to field some questions.
Thank you very much for your talk. We have 5 minutes of questions. Afterwards, we have a little bit of a longer break for the people that want to have, or we have a little bit of a longer break for the people that stay in this room than 5 minutes. For everyone that wants to go to the other room, we have a break of 5 minutes. This is because of the lunch queue, so we want to minimize that. So 5 minutes for questions. For everyone who sticks around in this room, we can do a little bit longer.
Thank you. So as I understood, if I understood correctly, the similarity measure between sentences is fully symmetric between sentences, right? So there's no notion of order. So it's a symmetric matrix that you're getting the eigenvector from in the end, so it's not really referral that you're measuring as such, because a sentence rarely refers to one further down in the text, I guess. So I'm not sure this is a question. Just
right. You're not sure the question is.
Yeah, just thinking out loud, really.
Either, so I'll just improvise a bit. So you're right that it's sort of a stretch to find out what exactly the relationship is between sentences in the text rank environment as opposed to websites in the PageRank environment. It's not actually specifically stated somewhere in that original paper. They just said, hey, we can use this algorithm if we do this to make a graph out of it. So I think you have to play a little fast and loose with this idea of relationship in sentences. It's just like there's this latent concept of one sentence referring to another based on information they're trying to convey on a very abstract level.
No.
And then trying to make that in some way concrete, you then resort to looking at the words in those sentences.
All right. Yeah. Thanks again.
Okay. So I'm going to count hands again. I see 1, 2, 3, 4 in the back, and 5. I'm going to do left to right. Makes it easier to walk.
Thank you for the amazing talk. I have a question. So when it comes to the similarity matrix used between sentences, you mentioned that Genzim is using by default TF-IDF, which solves some of the issues, as you mentioned. But using your example that you said C runs or C is running, this is solved by stemming, but what if you had the sentence C runs into the building and then he rushed into something else in the building? So TF-IDF would fail there, right? But what if you could use the doc2vec or some other representation that captures meaning rather than co-occurrence of words? Have you tried that?
No, I haven't tried that. A couple things at play here. One, I was looking for a fast tool because I was trying to see if I can put this in a system that just digests pieces of text really rapidly. So incorporating some larger model would really slow things down. For instance, you could even do something, before you even resorted to deep learning models, you can use lemmatization algorithms. But even that, I felt like, was too great a computational cost for the performance that we would get out. And then the last concern is that even if you were to use word2vec's focused on individual words, but then the context of those words is also important. And so you maybe want to convert your word into a sentence somehow, and your word vector into a sentence vector somehow, and that's also kind of an open problem. Oh, doc2vec. Oh, so I haven't used specifically doc2vec.
Okay. So we go to number 2.
Thanks. I also wanted to ask the doc2vector, yeah, but I asked. So another question is, I found something missing in the optimization. Like there are fixed phrases like United States, and if you separate the two words, they are totally different, meaning.
That's correct. And like I said, this is like an algorithm which plays off for computational cost, where like little accents like this. So if you're right, if one sentence says United States and the other sentence says America, you're not going to get a match. But hopefully there will be enough information surrounding those words, and if not, yeah, then it's not going to, for that pair of sentences, it's not going to work. But maybe those sentences won't be the most likely candidates for some extractive summarization algorithm anyway.
Okay.
Yeah.
We'll go to question number 3, so that's you.
I also wanted to ask about doc2vec.
doc2vec. So anyone else for doc2vec? Okay. If you could pass this on, that would be great. Yeah.
Hello, thanks for the talk. You compare PageRank with TextRank, and you said PageRank is sparsely connected graph.
Yep.
And there is like a random surfer model that some server will just randomly jump 15% of time.
Yep.
Will jump to some random nodes that's not connected. And with TextRank, you said it's densely connected graph. Does it mean it's fully connected, so all nodes, any pair of nodes are connected to each other?
Right.
Or
Yeah. So you start out with a fully connected graph,
Yeah.
like you said. Once you calculate these edge weights, hopefully a number of these edge weights will be 0, so you can view those
Okay.
as being removed from the graph.
Okay.
So that's, I think, specifically the
yeah.
question. But there's also that additional component where we had that random jumping. That random surfing component is also incorporated into the to the TextRank algorithm.
Also, there's also like a certain percentage that the node will just randomly.
And
Okay.
so your interpretation of this jump, like that two sentences don't actually share any words in common, but talk about the same concepts by chance, maybe you can view it that way. But like I mentioned in one of the previous questions, you have to play a little fast and loose with the analogy.
Yeah, thanks.
Okay, so then we'll quickly go to the last question. I'm sorry I can't incorporate you. I don't know if I missed you, or did you just raise your hand? Ah, okay, sorry. So
If we're out of time, we can also talk offline.
So my question is about the very last step. So I see how you rank the sentences on importance and relevance. But did you ever find that when you're picking the last sentences for the summary, that the sentences that were being picked were too similar to each other. For example, you have a document and they're talking about 3 different reasons why something is the case. Then a human would pick those 3 different reasons, I suppose. While if you use the algorithm and just pick the most relevant sentences, it might kind of be too similar to each other, the sentences you pick. Does that make sense?
It makes sense to me. I didn't personally encounter that problem.
Okay.
That may have done with the domain which I was focusing on, which is news articles. But because you can set your word limit, you can, if you start experiencing that, you can also just reduce the word count of the eventual summary, and hopefully that will decrease the chance that 2 sentences at the very end were quite similar to one another, or at least have similarity scores like one another, will not appear both in the summary.
Okay, thanks.
Okay, again, apologies I didn't see you there. Because of time issues, we have to conclude here. Thank you very much for your presentation. Please give him a warm applause.